Hi, welcome to this lesson about correlation. In the previous lessons, or rather modules, you explored variables, how data and surveys work, descriptive statistics, and much more. All of these topics are in preparation for the next modules. As a statistician and data analyst, a majority of my time is spent preparing the data collection, looking at our methodology, collecting the data, and cleaning and preparing the data for the analysis. Only 10 to 20% of time is spent on doing the actual statistical tests. This is because these statistical tests are, once you understand them, quite easy to perform. So you may have thought during the previous modules, when are we going to talk about statistical tests? Well, that's because a good start is half the battle. So without further ado, let's get into these statistical tests, starting with correlation. In the first lesson of this course, you learn about correlations using these misleading graphics. For instance, the correlation between per capita consumption of cheese and the number of civil engineering doctorates awarded. All of these examples have a very high correlation with each other, yet obviously have nothing to do with each other. It's like you've probably heard a million times before. Correlation does not equal causation. But then, what exactly is a correlation? When we talk about correlation, we're talking about the question, what is the strength of the association between two variables? For instance, let's say you have variables A and B. If a person who scores high on A also scores high on B, and another person who scores low on A also scores low on B, there might be a correlation between variables A and B. A common example that you've probably heard of before of correlated variables is the association between the job motivation of an employee and his or her performance. If the employee is highly motivated, he or she will most likely perform better in their job. Similarly, if they have low job motivation, they will most likely perform poorly in their job. Or, in a broader perspective, think of the correlation between the demand for a product and its price. When the demand for a product goes up, the price goes up as well. These are examples of positive correlation. You can also have a negative correlation, where scoring high on one variable means that you will likely score low on another variable, and vice versa. For instance, you can measure the amount of time employees use social media in the office and their productivity. When they are spending a lot of time on social media, they are likely to be less productive. And if they are spending little time on social media, they are often more productive. Both types of correlation can be measured using Pearson's R. Pearson's R uses the covariance in its formula, which is a measure of the joint variability. If the greater values of one variable mainly correspond with the greater values of another variable, and the same holds for the lesser values, like in our example between job motivation and performance, the covariance is positive. Pearson's R is obtained by dividing the covariance of the two variables by the product of their standard deviation. Now I could explain in detail how you should go about calculating it by hand, but then you would have to understand this formula. It's not something you will want to do, and you will never in your career calculate it by hand. That's why we have wonderful statistical programs such as R and SPSS to do the work for us. So, I want to talk about the results of Pearson's R, as well as a couple of things you have to keep in mind when performing this analysis. First of all, the outcome. After you've run your analysis, you get a value for Pearson's R. This value is always somewhere between -1 and +1. A -1 is a perfect negative correlation, whereas +1 is a perfect positive correlation. The closer R is to either +1 or -1, the more closely the two variables are related. Next, Pearson's R assumes that the relationship between variables A and B is a linear relationship. I will talk more about assumptions later in this lesson, but what this means is that for every increase in variable A, variable B goes up in a linear fashion. For instance, every point that variable A goes up, variable B goes up by 0.5 points. This way you can predict variable B from the score of variable A. It also allows us to use a best fit line in our scatter plot, which is a straight line that best fits all the data points of the two variables. This line may pass through some of the points, none of the points, or all of the points. To visualize this, we often use scatter plots. To help with the visuals, we also divide our image into two quadrants, both of which represent the mean for each respective variable. You don't normally do this, but we do this for explanatory reasons in this lesson. This image shows our previous example of the correlation between job motivation and performance. This is an example of a positive correlation. As job motivation goes up, So does performance. Our best fit line goes up from left to right, as most of the values fall in the bottom left and top right corner. This is because we expect with a strong positive relationship that if one of the variables scores low, the other variable also scores low, and the same for if one of the variables scores high. In this case, we don't expect many values to fall in the top left or bottom right, as that will mean a low score on one variable and a high score on another. However, we do expect this if the correlation is negative. This is often called an inverse correlation. For instance, as more employees are laid off, satisfaction among remaining employees decreases. Now, if R is close to 0, it means that there is no relationship between the variables. This can look something like this, where there is no discernible pattern. For instance, the saltiness of the soup in the cafeteria and the number of internal promotions. But what does it mean when you get an R of 0.4? Is that good or bad? For this, we often use the following rule of thumb. If your R is between 0.1 and 0.3, there is a small or weak correlation. If your R is between 0.3 and 0.5, there is a medium or moderate correlation. If your R is between 0.5 and 1, there is a large or strong correlation. So if you have an R of 0.4, you can say that you have a moderate correlation between your variables. However, this does not mean that it's automatically statistically significant. The significance level is influenced by two things: the strength of the effect and the sample size. A very strong effect requires a smaller sample to become significant than a weak effect, simply because a strong effect is less likely to happen by chance. In case you're exploring a weak effect, you will need a larger sample. Any weak effects will, at some point, become significant as long as the sample size is large enough. A funny example is that when you give an equal choice between two doors, one on the right and one on the left, right-handed people have a very, very small preference to go for the door on the left, and we only know this because it has been tested by thousands and thousands of people. This is an example of an irrelevant finding that turns significant because the sample is large enough. So the R value and statistical significances are far from the same. You can have a weak correlation, but still have a significant test result. A statistical significance test simply shows whether it's unlikely that this association between the two variables is due to chance. So to conclude, the size of R determines the strength of the association between the variables. The p-value that you get when you do a correlation analysis shows if there actually is an association. Remember therefore to always report both of them. Here you can see the output of a correlation table between several variables, namely managerial support, employee career development, rewards and recognitions, and employee engagement. You will first notice that all the variables are, obviously, fully correlated with themselves, which is the diagonal line from the top left to the bottom right. Next, you see that employee career development is highly correlated with managerial support, with the significance level of 0.01, which is one-tailed, at a Pearson's R of 0.648. Employee engagement is moderately correlated with managerial support, at a Pearson's R of 0.445 and a p-value of, again, less than 0.01. The other variables are, similar to employee career development and managerial support, also highly correlated with one another with a p-value of less than 0.01. The top right corner of the table is a direct mirror of the bottom left corner, meaning that you can, when you're reporting your own output, leave these values out, as they are redundant information. Next, there are several assumptions that have to be met before you're able to perform a Pearson's R correlation analysis. They are as follows. First, your two variables should be at the interval or ratio level, or in other words, they are continuous variables. Just to remind you of the previous lesson, these variables can be IQ, age, tenure, and so forth. Next, you want to make sure that there is a linear relationship between your two variables. Whilst there are a number of ways to check whether a linear relationship exists between your two variables, I suggest to simply create a scatter plot in your statistical program of choice. This doesn't mean that you only need a linear relationship between your variables. Exponential or logarithmic data can be transformed to become linear as well. The scatter plot will help in identifying the directionality of dissociation in your data. The following example shows why it's important to look at your data before you analyze it. This image shows scatter plots of Anscombe's quartet, a set of 4 different pairs of variables created by Francis Anscombe. The 4 y variables have the same mean, 7.5, variance, 4.12, correlation, 0.82, and best fit line. However, as can be seen on the plots, the distribution of the variables is very different. The first one, the top left, seems to be distributed normally and corresponds to what one would expect when considering two variables correlated and following the assumption of normality. The second one, top right, is not distributed normally. While an obvious relationship between the two variables can be observed, it is not linear. In this case, the Pearson correlation coefficient does not indicate that there is an exact functional relationship. Only the extent to which that relationship can be approximated by a linear relationship. In the third case, bottom left, the linear relationship is perfect, except for one outlier, which exerts enough influence to lower the correlation coefficient from 1 to 0.816. Finally, the fourth example, bottom right, shows another example when one outlier is enough to produce a high correlation coefficient, even though the relationship between the two variables is not linear. These examples indicate that the correlation coefficient, as a summary statistic, cannot replace visual examination of the data. Third, there should be no significant outliers. Pearson's R is sensitive to outliers, which can have a very large effect on the line of best fit, as seen in the previous example. Therefore, in some cases, including outliers in your analysis can lead to misleading results. It is best if there are no outliers or that they are kept to a minimum. Finally, your variables should be approximately normally distributed. Again, the effects of what can happen if this isn't the case can be seen in the examples that I showed you of Anscombe's quarter. After you've done your correlation analysis, in this case Pearson's R, you could get the following results in a correlation between IQ and performance. The important cells we want to look at are either B or C. Cells B and C are identical because they include information about the same pair of variables. Cells B and C contain the correlation coefficient for the correlation between IQ and performance, 0.513, its p-value, 0.001, and the number of observations that the calculation was based on, 354. The correlations in the main diagonals, cells A and D, are all equal to 1. This is because a variable is always perfectly correlated with itself. Based on the results, we can state the following. IQ and performance have a statistically significant linear relationship, as p is lower than 0.001. The direction of the relationship is positive, which means that IQ and performance are positively correlated. The magnitude or strength of the association is approximately moderate, as it's between 0.3 and 0.5. The last point that I want to make is that while correlation coefficients are normally reported as R is and then a value between -1 and +1, squaring them makes them much easier to understand. The square of the coefficient, or R square, is equal to the percent of the variation in one variable that is related to the variation in the other. An R of 0.5 means that 25% of the variation is related. 0.5 squared is 0.25. This means that, in case of a causal relationship, if you increase variable A by 1 point, you can explain 25% of the increase of variable B. An R value of 0.7 means 49% of the variance is related. 0.7 squared is 0.49. Or in other words, the change in both variables can be explained by 49% with the variation in the other variable. Almost 50% of the change in variable A is therefore caused by changes in variable B. This will only work in case of a causal relationship, of course. Correlation does not equal causation, so be very careful in interpreting these numbers. However, what happens when your data does not use interval variables? For instance, if you work at a professional service firm and you want to analyze in what way billable hours by accountants or lawyers are associated with other variables, such as engagement or proactiveness. Billable hours is usually divided into several groups, -15% to -10% on the norm, -10% to -5% on the norm which is between -5% and +5%, 5% to 10% above the norm, and so on. How can you relate this kind of data to a variable such as proactiveness? Well, this kind of data is ordinal. The groups do have an order, but they don't have proportionate intervals between variables. In this case, we cannot use Pearson's R, as it violates the first assumption we spoke about regarding interval or ratio variables. In this case, we need to use Spearman's rho. Spearman's rho is for data that does not follow the assumptions of Pearson's R. For instance, you can use ordinal data together with interval and ratio variables. Furthermore, your data does not have to follow a normal distribution, as the data is often used for non-parametric data. For instance, the top right example in Anscombe's quarter is a good example of non-parametric data. With Pearson's R, you wouldn't be able to find a relationship, as it assumes that there is a linear relationship. However, we can still clearly see that there is a relationship, only not linear. That's where you use Spearman's rho. Spearman's rho is often denoted by the Greek letter rho, or as r small s. It is quite similar to Pearson's R with regards to the way it is calculated, and the results that you will get. Spearman's rho will also be between -1 and +1. Simply select Spearman rho's instead of Pearson's R when doing your correlation analysis in your statistical program of choice. To help you with knowing when to use which statistical test, here you can see a picture which I will use in the next few lessons as well. You start on the left and, looking at your data, you simply follow the chart to get the statistical test you need. Well, that's it for this lesson. In this lesson, you learned about Pearson's R and how you should interpret it. You learned how to visualize correlations through the use of scatter plots and best fit line. Next, you learned about the assumptions for a correlation analysis, and you saw an example of the output of a correlation analysis. Finally, you learned about Spearman's rho and when you should use it. In the next lesson, we'll be taking a look at t-test, or as I like to call it, a match made in heaven. See you there.